Howdy folks, my name is Alex Wiseman, talking to you today about measures of variability. Let's count the ways we can have fun with that. Actually, I think it's very interesting because it's a way for us to describe our data and talk about the distribution of those scores, whatever they might be about, whether they're about education or health or community or politics, whatever kind of data we have. We've already talked in a previous set of screencasts about measures of central tendency. This time we're talking about measures of variability. So the ways that we describe our data can take kind of those two flavors. So variation is the most standard way that we think of measuring variation, and it's simply a way for us to begin the discussion about how far do scores deviate from the mean and how spread out are the scores. And so if you had a chance to look at the measures of central tendency screencast, you've already seen these little diagrams. But let's say we're plotting two variables, x and y, on a little scatter plot. And this is our population, or sorry, our sample A, this is our sample B. And we find that when we plot the scores for sample A, it looks something like this. This is simply, x here, y here, and then they meet here. And if we plotted them for sample B, they might look a little more like this. And if we take the average of all of these scores, we could draw a line. That would represent the average. I'm going to put mean, M for mean there. Right. And then simply we look at the distance between each of those individual scores and the mean. And this is when we did the deviation from the mean in our measures of central tendency screencast. And you can do the same thing over here. I'm not doing it very well, but you get the picture. And we can see that the distribution is much bigger on this side than on this side. In other words, the scores, the individual scores, are farther away from the mean for sample A than for sample B. And when we take the sum of the deviations from the mean, just the sum of the deviations, it always comes out to be 0. But if we square those deviations before we add them up, before we sum them, we come up with something called the sum of squares. And the sum of squares was a way for us to talk about how big the variation was when we were talking about measures of central tendency. Well, we're building on that now when we're talking about variation. Let me erase my ink. There we go. We're going to build on that, and we're going to talk about variance, which is simply the average squared deviation of scores from the mean. It's the average sum of squares. And the standard deviation is the square root of the variance. So you can see how we're kind of building. This is the average sum of squares. This is the square root of that. So very straightforwardly, how do we calculate our population variance? And by the way, we have a couple of different ways of talking about things in our sample and in our population. Right? Remember from one of my very first screencasts, we talked about how sometimes we use different statistical notation for the population and the variance to denote which one we're talking about. This is just a way of calculating a population variance. Let's say you have the whole population data. Right? We're going to calculate the mean. We're going to subtract the mean from each score, and of course it's going to be okay if some of the differences are negative, and we're going to square each difference. Right? Then we're going to add up all those squared differences. This is the sum of squares. We're going to divide that sum by the total number of scores. So this is the sum of squares divided by n. So we're taking the mean of the sum of squares. Okay? And remember, this is simply, sigma is summing. The x sub I means each individual score minus, and this is a symbol for the population mean. So we're squaring those deviations. You can see the square there. Well, maybe you can't under all the red ink now. And then we're dividing by n. If you want to take the sample variance, there's a slight difference. Right? You calculate the mean, subtract the mean, square each difference, add all the squared differences. Sum of squares just like before. By the way, little different notation. We're using the S and we're using the M instead of here we're using the fancy sigma and the fancy upsilon. I think that's an upsilon. But here we're going to do something different. We're going to divide the total number of scores minus 1. So this n minus 1. This is called degrees of freedom. And then your answer will be the variance of sample scores. So it's the same as calculating the population variance, except instead of dividing just by n, we're dividing by n minus 1 because of this degrees of freedom idea that we have with samples. Now, degrees of freedom are an interesting concept, and it's always the sample size minus 1. Well, it's typically the sample size minus 1. There are differences when we get more advanced in statistics. But it is simply the number of values in a set of scores that are free to vary after certain restrictions are placed on the data. Now, you'll remember that our deviations from the mean always add up. The sum of deviations from the mean always adds up to 0. That's why we square them when we're creating the sum of squares and then variance and then standard deviation. Right? Because the sum of deviations from the mean is always 0, there's no, this is the way you have to think with me a little bit, there's no freedom to vary because it always must add up to 0. Right? If we know all the scores and thus all the deviations but 1, however, we can easily calculate the last score and the deviation. So we want to take 1 out of the mix. So there's a little bit of play left. That's why we need a little bit of freedom to vary when we have a sample. Because remember, we don't have the whole population data. We're not exactly sure what everything looks like when we have a sample. So we have to have some opportunity for our results to vary. And so we subtract 1 from n to get our degrees of freedom, and then we use that when we calculate the standard deviation. Now, in this class, or when you work with me, or however you want to think about it, we often calculate this using a statistical software program like SPSS or something like that. So you will rarely be doing these hand calculations. But I think it's important to understand how this works, that we have the sum of squares, that we're taking the average of that for the population variance, that we're taking the average of that using degrees of freedom, the n minus 1 for the sample variance, and that you understand sort of why we have this degrees of freedom concept. Now, there's a little difference if we're calculating the variance of dichotomous variables like gender. And again, if you watched my measures of central tendency screencast, you saw that usually for nominal variables, mode, or counting frequency, is really the only appropriate measure of central tendency. But when you have dichotomous variables, you can take a mean because it will give you a proportion. So it's a little bit of an exception to the rule. And as a result, calculating the variance of dichotomous variables is different than calculating the variance of interval and ratio variables. And it's very simple, right? The proportion is simply we add all these scores up and divide by n. So it's the sum of xi divided by n. Right? It's the mean. That for dichotomous variables will give you the proportion for this set of scores that happens to be 0.4. To calculate the variance of this dichotomous variable, we are simply going to follow this calculation. And again, you can do this automatically with SPSS if you're using it or any other statistical software program. But it's simply the proportion times 1 minus the proportion. So 0.4 times 1 minus 0.4 is 0.4 times 0.6 is 0.24. Ta-da! And that gives you a coefficient that is the variance of the dichotomous variable. Right? Handy to know, just lets you know that there's something unique about dichotomous variables to be aware of, that they're a little bit of an exception, and we do run into them quite a bit in social science research, especially in comparative and international education. Now, if we want to take it a step further and go from calculating variance to calculating standard deviation for the regular thing, we're not talking about dichotomous variables anymore. We compute the variance, which you just did, and we find the square root of the variance. And then you have a standard deviation. It's literally that simple. Right? The idea, oh, I went too fast. The idea is that you're trying to find a way to look at the variance that makes sense in relationship to your distribution of scores. And remember, we've already talked again in previous screencasts about the bell curve and the distribution of scores that we're always trying to sort of compare our own sample against. So what our standard deviation does when we find the square root of our variance, it gives us a way to think about how far, from the mean most of or much of our set of scores lies. So you can think of it this way. This is 1, 2, 3 standard deviations from the mean. Remember, the mean in a normal distribution, mean, median, and mode in a normal distribution are always in the middle. This is 1 below, 2 below, 3 standard deviations below the mean. So it's a way for us to begin to visualize and to begin to conceptualize what that variation looks like. Now let's just think of some big questions just to get an idea about what variance and standard deviation sort of means. Let's say we have a data set for the 50 United States, right? And the standard deviation for subscription rates to the Comparative Education Review, subscribers per 100,000, is 308.1. Right? That's our standard deviation, let's say, for Comparative Education Review subscription rates. But the standard deviation for another journal that we look at in our field, Prospects, for the 50 states is 229.2. Right, now you have two, at this point they may seem relatively random numbers representing the standard deviations for subscription rates between two different professional journals in comparative and international education. So what does this difference in standard deviations imply about geographic differences in the appeal of these two, I should say journals, not magazines? What does it mean? So one is 308 and one is 229. So what? Well, the answer is pretty straightforward. It simply means that the popularity of the Comparative Education Review varies more widely across states than does the popularity of Prospects. This is a larger variation across the U.S., across the United States, all 50 states, whereas Prospects is more limited. It suggests that there is a wider distribution of subscribers across the United States to the Comparative Ed Review than there is to Prospects. And if we were able to visualize this, and I don't have a visualization for you, but if we were able to visualize this, we might see that the Comparative Education Review subscribers were located in cities all across the United States, whereas, and I'm making this up because I don't have data, but we might see that Prospects subscribers were mostly east of the Mississippi River, most in the eastern half of the United States. How about another one? Consider this argument. The standard deviation of enrolled students' age in the United States is higher than the standard deviation of enrolled students' age in Mexico because there are many more people in the United States than in Mexico. So of course the standard deviation of age is higher. Well, is that a valid argument? Is that true? Is it not true? And why? Again, the answer is very straightforward. That's not a valid argument. Variation does not depend on the size of a population, and in fact, a small population often varies more than a large population. And that we should put stars behind. That is really important, and that's one of the reasons why we try to have larger sample sizes when we want to compute statistics, because it helps us reduce overall variation, it helps us account for more representation. I mean, many reasons I could go on, but this is an important one to remember. And then finally, this is a kind of a silly question, but I think it's an interesting one. If a man was drowned crossing a stream that was on average only 6 inches deep, and remember, that's not very deep, so it would be hard to drown in that. Which of the following streams did that man cross, and how do you know? Well, here we have the width, the depth on average, and the standard deviation of the depth of the River Styx, the River Stones, and the River Phoenix. Right? Which one did the man drown in? Well, I'll give you the key. They're all 6 inches deep. Width is there. But most importantly, look at this. 3 feet standard deviation for the River Phoenix. Guess what? A standard deviation that is large implies some parts of the river are quite deep or deviate significantly from the mean. Now you know a little bit about variability. Come back for screencast number 2 and we'll talk about more.